have the problem of a car or cart going up a hill or a small incline, and it has a piece of felt that's causing friction on the bottom of it. And this cart is going up at a small incline of theta. And then the car comes back down the same hill at the same incline. So here's the free body diagram of the cart, acting opposed to the motion of the cart. We have the normal force acting perpendicular to the surface of the small incline. And then we have gravity acting on the cart, pulling it straight down. Now we need to find the angle at which the cart is going up the hill. So first we're going to write out our so that way we don't get mixed up on our sines, cosine. We're going to mark out which ones are which. And now we're going to set our origins. That way we know that that is what our axis is going to be. So we know that the summation of forces is equivalent to mass times acceleration. So, the summation of the forces in the y direction are mass times acceleration in the y direction. I'm getting ahead of myself. Acceleration in the y direction in our problem is 0. So, when you times the mass by 0, this goes out to 0. Now we need to do the forces in the x direction. So we have mass times acceleration in the x direction. So first we have the negative force of friction acting on the negative force of gravity in the sine theta. And this is equivalent to mass times acceleration in the x direction. As she's written out, mass in this problem does get canceled out. This leaves you our acceleration while the cart is going up the hill of gravity times sine theta plus the coefficient of friction times gravity times cosine theta. And we're just going to pull the g out just to make things simpler. And we do this because the g is a constant. So now we need to do the equations for the cart going down the hill. So first we're going to draw the problem. still have the same theta as we did in the cart going up the hill. Now we need the free body diagram so that way we can properly see what we're working with. So just like with the last problem, we have friction acting in the opposite direction of the moving cart. And then we have the normal force still acting perpendicular to the surface that it is on. And then we have gravity acting on the cart as well. Now we're going to find the cosine of the sines, so that way they are not confused. And now we're going to set our axis, and it's still going to be the same as our previous problem, where the axis is it's perpendicular to the surface of the incline. So we know that the acceleration of y equals 0, just like that we found in our previous counter. So now we need to find the forces acting in the x direction. So we know that the summation of forces acting in the x direction is still mass times acceleration in the x direction. So we substitute in the proper information for our summation of x forces, which is gravity times sine theta minus the force of friction, and this is equivalent to the mass times acceleration in the x direction. Alright, so now we need to rework the problems that we are solving for the force of friction. And now we need to solve for acceleration in the downward descent of the cart. Which this comes out to gravity times sine theta minus the coefficient of friction times cosine theta. So we're just going to take out the constant of gravity again, so that way things are more simplified. Now we get to the final parts of this. We need to take the equation for our acceleration in the upward moment, or the upward ascent of our cart, minus the acceleration in the downward descent of our cart in the x direction, because our y direction is 0. It's been canceled out. And we divide this by 2 cosine theta. And this is equivalent to our coefficient of friction. Which is what we're looking for, because as we remember from the beginning of this, we are looking for the coefficient of friction of the small piece of felt that is acting on this cart. Alright, stop. Now that we have our equation, we need to plug in our information. So the acceleration of the cart in the upward direction of the inclined hill is 0.4786, and the acceleration of the cart in the downward direction is 0.4176. Now we divide this by 2 times gravity times cosine theta, and theta is 1 degrees. So when you plug this into your calculator, you find that the coefficient of friction of this piece of felt comes out to 0.00392. There you go. Okay, so the way we find our information for our acceleration values, we first highlight the cart going up the hill on our Logger Pro. Then we fit the curve to a quadratic and find the min and the max on the upward incline of the hill. And then we do the same thing for the decline of the cart. As you can see, it changes the values whenever you try both sides. We then take these the values that we get off of Logger Pro to find our percent errors for both sides, and then we find the medians for the mins and the max to find our accelerations in the upward direction and the downward direction. To find the angle of the incline, we took the video we have here and put it into Logger Pro. We've set that this distance is 1 meter from here to here, and this is our axis of origin. And then we use the program itself to tell us that this distance to the origin of 1 meter is 0.9981 meters. We then use the function of cosine, which is adjacent over hypotenuse, to find that the angle is 0.9981 meters.